This is the second video in the Simio Modeling Framework module, and in this video we'll cover three basic topics. The topic of properties and states, the use of objects as resources, and finally Simio stations. So properties and states tend to be one of the more confusing topics to users who are new to Simio. It's not the notion of what a property or state is, it's what the difference is and when to use one versus the other. And so we'll continue to come back to this notion as we move through the modules. And what we'll do here is we'll just provide some definitional information. So a property is a static attribute and doesn't change during a run. So some of the examples that we have are processing time, failure rate, initial speed, batch size, cost per hour, and so on. A state, on the other hand, is a dynamic attribute, and it can change during the run. And so examples of that include processing count, the number of failures, current speed, batch size, accrued cost, and so on. And so when we differentiate between properties and state, both are attributes. Property is static, and a state is dynamic. So let's look at properties first. So properties are strongly typed, meaning each property is a particular type, and there are lots of different types that we'll see as we continue to enhance our modeling skills. So we have so-called standard properties where we have integer, reals, expressions, booleans, and so on, and there are 20 of those. A property can be an element. We talked about elements in the previous video in this module. A property can be an object, and it can either be a generic object or a specific object. So I can give it a specific object type or just the generic object reference. It can also be something called a repeat group, which allows me to have sets of any of the above combined together into a single group. Now the notion here that a property cannot change definition during a run is a little bit confusing. So let's take a look. Let me open Simio here and let's take a look at a specific example of that. So let's grab a server object, and what I want to focus on is the property of processing time first. And so you can see that we have processing time set to random.triangular 0.1, 0.2, 0.3 minutes, and so that says every time an entity is being processed by the server, we're going to sample from this probability distribution to get the actual delay time. And so that notion of sampling, again, tends to confuse new users in the terms of what can and cannot change. So while the definition can't change, the actual evaluation or the instance will change in the case where you're sampling from a random probability distribution. So for example, the first entity that uses the server might sample 0.125 minutes, the second one 0.225 minutes, the third one 0.228 minutes, and so on. So the actual values that are sampled change, but the key fact here is that the object definition or the property definition does not change. The property definition is that random dot triangular, so it defines that probability distribution. And so back in Simio, we can see the other properties associated with the server 1 instance also don't change during the run. So for example, the transfer in time will always be 0. That won't change. The capacity type will always be fixed. That can't change, and so on throughout the model. So states, on the other hand, are dynamic, and states can change during the model run. And so if we want to have something like mention processing count, so we're going to count the number of entities, that's obviously going to change as the model progresses. So we differentiate states into two basic types. We have discrete states and level states, and then we have a subcategory of level with acceleration. So discrete states change values only when assigned. So at discrete points in time, they change values. Discrete states can either be scalars or arrays, and you can have up to 10-dimensional arrays. And the types of values that we have are real, integer, boolean, date time, list, string, element reference, object reference, and list reference. For a level, the value changes continuously over time. So you set the level parameters, and Simio changes the value continuously over time. Level with acceleration is similar, except it also has an acceleration component that lets you change the value with an acceleration. And so if we look at these three, if we just compare these three, so we have red is a discrete state, The blue is a level, and the gold is a level with acceleration. You can see here at time 5 minutes, we set the state value to 10. So it immediately jumped from 0 to 10 at that same point in time. We also set level 1 to have a rate of 10. That's the blue one. And then level 2, we assigned an acceleration and an acceleration duration of 30. So if we jump ahead to the end of the acceleration duration here at 35 minutes, you can see that the rate or the value has continuously accelerated until we get to 35 minutes, and then it stops. For the blue, for the level, we can see that the level has continuously changed at the same rate, the rate of 10 over that time. And then at time 60 minutes, we changed the value of the discrete state to 0, and then we set the the change rates for the levels to 0. And so you can see at time 60, the discrete state jumped back down to 0, and the two levels leveled off. So they set the rate of change equal to 0, and so they just maintained their current value. So object definitions can have both predefined and optionally user-added properties and states. And so the designer of an object, the person who implemented an object, whether they're standard library objects that were implemented by Simio or custom objects developed by a user, the predefined properties and states will be defined by the designer, and then that can be extended by the user. States and properties of an entity are sometimes referred to as attributes of that entity. And so the state attributes are the ones that change during the run, and the property attributes are the ones that don't change. And so people sometimes refer to these as attributes of the entity, whereas states and properties of a model are sometimes referred to as global variables for that model. So we think about something like the number of parts produced would be considered a global variable, and the implementation would be a model state. States can also be defined on other object definitions, such as the two examples that we have here, like an accrued cost on a server or the total travel time for a vehicle. So in Simio, any object can declare itself as a resource. So let's see what that means. Let's go back to Simio and let's build a very simple source server sync model. So there's my source, there's my server, there's my sync. Let's connect these guys up using paths. So there to there, and there to there. So we have our simple model, and we'll just click run. And when we watch this model run, the question is, well, what causes this queuing here? What causes these entities to wait? And so what happens, let's see if I can get a queue there before I stop it. There we go. This entity is waiting for this entity, and so that implementation, this server is a resource, and the entity needs to seize the resource in order to progress. And so the basic logic says, come to the input, seize a unit of capacity of the server, and then delay for some period of time. If, when the entity arrives, there's not a unit of capacity of the resource available, then it just waits. So in this implementation, or in this case, this entity is waiting for this entity. When this entity releases the resource, then this entity can seize that resource. And so that notion of having a resource that has a capacity, it allows us to control access to resources that have this finite capacity for serving entities. And so, as I said, in Simio, any object can declare itself as a resource, and resources can be seized by multiple entities. And so this is a little bit of a strange notion when you think about having an entity seizing perhaps, say, another entity, but that's perfectly allowable, and often that flexibility is quite useful. Seizing and reallocation, let's go back and look at the model that we just built. And we talked about the notion of seizing, so when an entity arrives, it seizes a unit of capacity of the resource and it can't progress until one is available. The notion of reallocation basically says when a unit becomes available, so a unit of capacity of server 1, so for example, when this entity finishes and releases that resource, the server automatically reallocates the capacity to any entities that are waiting. And so that process has several different options that you can control through the object. A general reallocation rule basically says take the first one, first come, first serve. And so whoever got there first gets the unit of capacity, but that can be explicitly controlled and changed by the user. Advanced options also allow you to momentarily delay that so that you can account for events that happen simultaneously. And we'll see examples of that a little bit later on in the training. So more on resources. When we think about how this works, how this seizing and reallocation works, seize requests in something called an allocation queue of an object. So we have an allocation queue here. And when a reallocation happens, the entities in the allocation queue are considered to be allocated or to be considered for accessing unit of capacity. An important concept also for Simio is that the seize request can be rejected by the resource object, so-called smart resources. So I might seize an object, a server, and the server looks and for whatever reason says, no, I'm going to reject that seize request because maybe it's waiting for something else or something else depending on the situation. But that ability to reject a seize request is a powerful feature of Simio. And finally, a seize request or a seize step might be accompanied by something called a visit request. And a visit request says, I want to, for example, have the resource visit a particular node prior to continuing on in the process. So for example, when you look here, we have seizing object A, seizing object B, seizing object C. So object A also included a visit request. So object A now has seized the resource and is waiting for a visit. Entities B and C then also seized the object resource, and so they're in the allocation queue. So entity A holds the resource. Entities B and C are in the allocation queue, and object A is waiting for a visit request, and we're waiting for the object to visit a particular node. And so these are quite useful when we talk about having transporters and workers that move entities around in the system. And finally, for this video, we have the concept of a Simio station. In Simio, entities can either travel on networks, nodes, or paths. They can travel in free space, or they can visit fixed objects. And so when an entity visits a fixed object, it's located at a station within that object. Entities enter and depart objects at associated nodes. So we can see the associated nodes here. And this sort of generic object has the station A and station B. Stations have capacity that limits transfers into the station. So I can say this one has capacity 1, and for example, this one has capacity 2. And finally, entities reside in the contents queue of a station. So in this case, I have station A of this object has 2 entities that are visiting that station, and they're both shown in the contents queue. And so the standard server object is implemented using 3 stations. So you can see we have an input buffer, a processing, and an output buffer. And then we have an input node and an output node. If we look at that same thing in Simio, we can see, oops, let me jump back to our facility. Here's a server, and here is the input buffer content. So this is the queue that shows the contents of the input buffer station. Processing contents, which is the queue that shows the contents of the processing station. And finally, the output buffer contents or output buffer queue, which shows the contents of the output buffer station. And so as entities move through the model, they come off the network or out of free space into the input node, then transferred into the input buffer if there's capacity, transferred to the processing station once there's capacity, transferred to the output buffer once there's capacity, and then through the output node back onto the network or back into free space.